The world around us feels so solid, so stable, so predictable. But what if I told you that inside every single object you can touch, there is a hidden universe of perfect order, and sometimes utter chaos, and that battle defines everything about it. So let's dive into that world. So let's kick things off with a real head scratcher. On one hand, you've got a diamond. We all know it's the hardest natural substance out there. And on the other, you have the graphite in your pencil, which is so soft it just flakes off onto paper. What's the deal? And here's the kicker. They're both made of the exact same thing. Pure carbon atoms, just that. So you gotta ask, how can this same single ingredient produce such wildly different results? Well, the answer is hidden deep inside, in their internal structure. To solve this puzzle, we need to zoom in. I mean, way, way in. And the first thing you see when you zoom in is that solid isn't just one thing. Solids are actually divided into two very, very different camps. Okay, so solids basically split into two big groups. On one side, you have your crystalline solids. That's where all the atoms are arranged in a super ordered repeating pattern. But on the other side, you've got amorphous solids, where the atoms are kind of just jumbled together with no real long-term structure at all. Crystalline solids, these guys are all about what we call long-range order. Seriously, think of their atoms like soldiers in a perfect formation. If you know where just a few of them are standing, you can predict the exact position of any other soldier in the entire army. It's that predictable. But then you've got amorphous solids, and they only have short-range order. They're more like a disorganized crowd at a concert. Yeah, you might see a few small groups of people standing together, but there's no overall pattern. Their structure is actually a lot more like a liquid that's been frozen in place. And this difference on the inside, it has huge effects on the outside that we can totally see and measure. Just think about melting. A crystalline solid, like a good old ice cube, has a super precise melting point, 0 degrees Celsius. Boom, it turns to water. But an amorphous solid, like glass or plastic, it doesn't really have a sharp melting point. It just gets softer and softer and softer as you heat it up. All right, so for the rest of our journey here, we're going to focus on those super orderly crystalline solids. And it turns out, even they can be sorted into 4 main families, and it all depends on the type of glue that's holding their atoms together. First up, we've got molecular solids. And the perfect example is ice. Here, the building blocks are individual water molecules, right? H2O. Now, the bonds inside each little water molecule are incredibly strong, but the forces holding one molecule to another, they're pretty weak. And that's why ice is, relatively soft and melts at a pretty low temperature. Okay, next up, ionic solids. Think table salt. In this case, you have positive sodium ions and negative chloride ions, and they're all locked into this rigid grid by a really powerful electrostatic attraction. The classic opposites attract. And this powerful glue makes them really hard and brittle with super high melting points. Third, we've got metallic solids, and man, their setup is just something else. Try to picture this. You've got a fixed grid of positive metal ions, just kind of sitting there, but their outermost electrons aren't tied down to any single atom. Instead, they form this free-flowing, mobile sea of electrons that just zips around the entire solid. And that one simple idea, that sea of electrons, it explains everything that makes a metal, well, a metal. Why do they conduct electricity? It's just that sea of electrons flowing. Why do they conduct heat so well? Same reason. Those mobile electrons spread the energy around super fast. Their shine? That's the electrons reflecting right. And the fact you can hammer them into shape? The ions can just slide past each other inside that electron sea without shattering the whole thing. It's brilliant. And that brings us to our fourth and final family, covalent network solids. In these materials, every single atom is bonded to its neighbors with ridiculously strong covalent bonds. It's not really a collection of molecules. The entire crystal is basically one giant molecule. This makes them exceptionally hard with sky-high melting points. And yep, you guessed it, diamond is the poster child for this category. Okay, so we've got our 4 families, right? All defined by their atomic glue. But how are the atoms actually arranged in space? To understand that, we gotta zoom in just one more level to find the fundamental blueprint that all crystals share. The best way to think about this is like tiling a floor. The imaginary grid of points where you're gonna place each tile, that's what we call the lattice. It's like a scaffold. And the actual tile you use, the thing you place on that scaffold, which could be an atom or a molecule, That's called the motif. So here's the big takeaway. It's a super simple formula. You take a motif, an atom, or maybe a little group of atoms, and you place it on every single point of a lattice. And what you get is a perfect, repeating crystal structure. It's really that simple. Now, if you look closely at that lattice, you can find the smallest repeating chunk that contains the full pattern of the whole thing. We call that the unit cell. It's just like a single Lego brick. You can take that one brick, and by repeating it over and over again in 3 dimensions, you can build an entire castle. Okay, but here is where things get absolutely wild. I mean, think about all the endless variety of crystals out there in the universe. How many possible 3D lattice blueprints, how many fundamental patterns do you think exist? A million? A billion? The answer is just 14. That's it. Every single crystal that has ever existed is built on one of these 14 fundamental patterns, which are known as the Bravais lattices. All right, we've got all our puzzle pieces on the table now. We have crystalline solids, we have the 4 families, and we have this whole lattice and motif blueprint. Let's put it all together and finally solve our mystery. So let's circle all the way back to where we started. Diamond and graphite. We know they're both pure carbon, and we now know they both belong to that covalent network family. So what gives? And here it is, the answer. It's all about the lattice, how those carbon atoms are arranged. In a diamond, each carbon atom is bonded to 4 others, and they form this rigid, interlocking 3D network. It's incredibly strong in every direction. But in graphite, the carbon atoms form these flat, hexagonal sheets. Now, the bonds within the sheets are strong, but the forces between the sheets are super weak, so they just slide right past each other. And that's why graphite is soft and slippery. And this isn't just, a neat piece of trivia. Understanding this deep connection between the internal structure and the properties we see on the outside, well, that's the entire foundation of modern material science. It's literally how we design and build the future. Because once you know how to play with these atomic arrangements, you can create some truly incredible stuff. Carbon nanotubes, which are basically just rolled up sheets of graphite, can be tougher than steel. We can create high-temperature superconductors, new biocompliant solids for medical implants, and way better solar panels, all by controlling the structure at the atomic level. So the next time you pick up a pencil or, admire a diamond, I want you to remember that hidden world inside. It's a universe of order and design, a set of atomic Legos that we're really just now learning how to master. And it leaves us with one heck of a question. Now that we know the rules of the blueprint, what are we going to build next?